Hello and welcome to Infrared Radiation. This is Waves Lesson 8. My name's Mr. Pratt and I'm Science Director. Off we go. For this lesson you'll need pen, paper and exercise book, and unless you're actually watching this video on your mobile phone, get it out of the way, turn it over, put it on silent. Okay, so straight away into the starter, I want you to list factors that would affect the rate at which a bowl of soup cools. So possibly 3 things that might affect how quickly it cools down. I'll just give you 1 minute. Okay, so you might have listed perhaps the material that the bowl was made out of. You might have listed the area, the surface area of the soup. That's quite a large surface area on that bowl. Maybe the temperature. Maybe the temperature of the room as well as the temperature of the soup. For the challenge outcome, use accurate observations to determine which surfaces are better emitters of infrared radiation. I will break down there's quite a lot of keywords. I'll break it down in the first few minutes of this lesson, what all the different words mean there. But it's a required practical where we're looking at the amount of infrared radiation that's coming off different surfaces. So the Aspire outcome will actually be able to explain why we get different rates of energy loss from different objects, and we're going to use emission of infrared radiation. We probably will use absorption as well in a little bit of an application question later. So what I want you to do then, two little sections here. I want you to sketch electromagnetic spectrum, so just on a piece of paper, and label the types of radiation. You should remember 7 from a previous lesson, and describe the location. In other words, the order. If you could just put them in order, that would do. And I'm going to give you a minute. Let's try and do it quick. .20 seconds. Okay, let's have a look. So we've got a diagram there, and that's showing that on the left there the wavelength is greater, and then as we move along to the right, wavelength gets shorter, so they're getting closer together. That also means that down this right hand side where the wavelength is smaller, the frequency is greater. We've got more waves per second. So infrared in that spectrum is going to be about there. So visible light, if we put it in the middle, red, orange, green, yellow, blue, indigo, violet. Infrared on the left with a bigger wavelength than visible light, and then ultraviolet with a smaller wavelength than visible light. Radio waves, biggest wavelength, then microwaves, smallest wavelength, but biggest frequency, gamma and X-rays. if you were to look at that through your eyes, you would see the colours, obviously, you'd see the visible light, and then it would tail off to black. There are quite a few insects, particularly, that can see some of those wavelengths of infrared, not all the way along, but just on that edge of the red there.
Okay, so we've got this kettle that's just boiling. So this kettle, probably the water inside it's around about 90, 95, 96 degrees C, so it should click itself off in a minute. So I want to just try and work out exactly what infrared radiation is. So all objects that have got a temperature above minus 273, don't need to know that number, but all objects that have got some sort of temperature are giving off infrared radiation. So you can't see it because its wavelength is greater than the human eye can detect. So this kettle now is hotter than the environment. So it's giving off heat. It's transferring heat away from it in 3 different ways. So the first way that it's transferring heat away, if I carefully touch it, there, ow, if I touch that, that's transferring heat energy directly into my hand through the surface. So because I'm touching it, that's called conduction. So that's conduction of heat as I touch it. So it's losing heat that way, it's transferring it to the environment through the casing. If I just carefully pop the lid off and put my hand above it, feels very hot. You can see the vapour rising. So there, it's hot. It's hot because we've got heat being transferred from the hot water inside by convection. So the air above it heats up, becomes less dense and rises. So that's convection. Both conduction and convection require particles to do it. That leaves the last one, heat radiation. If I hold my hand close to the surface, but not touching it, the back of my hand's a little bit more sensitive, is there, I can feel heat there. I'm not touching it, so it's not conduction. I'm not above it, it's not convection. So there, the surface is transferring electromagnetic waves away. So it's losing energy that way. And that's infrared radiation. So that's infrared. So conduction, convection, radiation, waves that you can't see. Okay?
So then, question 2A, 2B, looking at those two there, you might be taking a bit of a punt at this. Don't spend too long. Fast forward if you haven't got a clue, because I will explain it later, but some of you might. So which teapot will keep your tea hottest for longer? So the black teapot on the left, pottery, the stainless steel teapot on the right. So 50-50 guess, and then explain why. I'm not going to give you long just in case you're struggling, so just a minute from now. Go on, that's long enough. So if you've gone for the black pottery teapot, you're wrong. So in theory, it should be the stainless steel teapot on the right. If you were to put identical temperature water from the kettle into both, and you were to hold your hand, the back of your hand, like I did, 1 millimetre from both, you would actually feel the black teapot would be giving off more heat. It would be emitting more infrared radiation than the stainless steel shiny silver coloured one on the right. So that's why, because it's emitting less heat radiation, it should keep your tea hotter for longer, which is to do with what the required So in the required practical, you've got to investigate the amount of infrared radiation absorbed and radiated by a surface. You've got to see how that depends on the nature of that surface. So that's quite complex. So let's break it down a bit. So we know what infrared radiation is. So infrared radiation is heat radiation. So it's part of the electromagnetic spectrum. Hopefully you'll be able to put down where it is. It's next to visible light and its wavelength is larger than visible light, so we can't see it. So we know what infrared is. Absorbed. Absorbed means that the infrared radiation is going into a surface. And radiated means coming out. A radiator should be putting heat into your room. So radiated means that the infrared radiation is leaving the surface. So the first practical that I'm going to show you is about radiation leaving a surface, and the second practical about radiation being absorbed by a surface.
Right, so just bring the kettle to the boil. This piece of apparatus is called a Leslie's cube. I don't quite know much about Leslie apart from the fact that he came up with this bit of apparatus. So metal, 4 different coloured sides, matte black, shiny black, silvered and white. So water boiling, that should be somewhere in the 90s. Fill that up, hope it doesn't leak. And within 20 seconds or so, all the metal of that cube will reach the same temperature. So the whole metal cube is at the same temperature. So what we want to look at is the amount of infrared radiation that's being emitted from each side. So we're going to use an infrared thermometer, and from the infrared thermometer we're just going to read the temperature of each one. So we'll do matte black first, if I can do it without burning my fingers. So matte black, (83.8 degrees C. Shiny black next. I want to try and be quick because obviously this could be cooling down now, so I want to be fairly quick. 74.0. White. Down at 45.2. Probably starting to make your own conclusions already. And then lastly, silvered. I've put a bit of foil on that just to make it a bit more silvered than it was before. A lot lower, 31.3. Right, don't need to record those numbers because they'll be on the PowerPoint in a minute. Be thinking about what your own conclusions are. So we've got a radiant heater, which I'll just flick it around so you can see, is giving off some red light, but also it's giving off infrared. So I can feel the infrared radiation there, pretty hot. So I've got 4 boiling tubes, equal volumes of water. Starting temperature of the water in all 4 of them is 20 degrees C. I've kept them equal distances away from the radiant heater. The only thing that's different, or the only thing that should be different, is the surface that we've got. So we've got matte black, shiny black, silvered and white. So you should be getting the hang of this now. We've got a difference between emitters and this time absorbers. These are going to heat up because they're going to absorb infrared radiation from this radiant heater. So what I'm going to do is I'm going to start the temperatures off, start that off, timer off, and I'm going to leave that recording for 10 minutes, and after that 10 minutes I'm going to record the temperature again and I'm going to write down the temperature rise. You don't need to record the temperature rise because it'll appear on the PowerPoint when I've finished. Okay, just getting up to 10 minutes. 10 minutes, right, so let's have a look at the temperature rise. So starting with matte black. So the matte black has gone up 14 degrees C. The shiny black has gone up 20 to 30, that's 10 degrees C. Oh, I've written that in the wrong place. 10 degrees C. No, I haven't written matte black twice, that should be white. So the white one has gone up, not as much, just 4 degrees.
and then the shiny silver. Some of you should be making a prediction. Just gone up the 1 degree C in 10 minutes. So matte black the most, shiny silver the least. Okay, so I've recorded the results there on this results table so that you don't have to jot them down. We can just have a look at them. So part 1 then, the Leslie's cube. So quick diagram just to remind you, metal box, different coloured sides, stopper in the top, hot water from the kettle, infrared detector, so it can measure the amount of infrared radiation that is being emitted. So question 3, explain what these observations tell us about the effect of different surfaces on the emission. So you need to talk about the different colours and talk about which are emitting the most. 1 minute. Seconds. Given a table on the exam with numbers in it, make sure that you quote the numbers as part of your explanation. Right, okay, from that we can see, so the one with the biggest temperature, so that's the matte black. So we can say then that with a temperature of 83.8 degrees C, the matte black surface is emitting the most infrared radiation. It's got to be a mark. So then we can go down to the lowest number and we can say the shiny silver surface with a temperature of 31.3 degrees C is emitting the least amount of infrared radiation, with shiny black, matte white being in the middle. Okay, so matte, that means not shiny, black surfaces emit the most amount of infrared radiation. So part 2 then, so there we've got 4 boiling tubes next to the infrared lamp. So we've got the matte black's gone up by 14, shiny silver's only gone up by 1. So now, question 3, why were these temperatures only recorded to the nearest degree C, but we used 0.1 degrees C a second ago? That's question 3. And question 4, explain what these observations tell us about the effect of different surfaces on the absorption of infrared radiation. So this time we're talking about absorption, heat radiation being absorbed going into the surface. I'm going to give you 90 seconds. Okay, I'm just going to give you another 30 seconds. Okay, see how you've done. So question 3. So we'd say with the thermometer that we've used to measure that temperature rise there, should say temperature rise and not heat rise, is it only had a resolution of 1 degree C, which means the nearest it can measure to is 1 degree C. It's the smallest line, if you like, is the 1 degree C line. Whereas on the digital thermometer before, it measured to a resolution of 0.1 degrees C, so we wouldn't put any extra numbers down. And question 4, let's do what I did before, let's use the numbers. So we'd say the matte black with a temperature rise of 14 degrees C is the best absorber of infrared radiation. And the shiny silver surface with a temperature rise of only 1 degree C is the worst absorber. So we've got a pattern. We've got matte black is the best absorber and the best emitter of infrared radiation. So a couple of questions on control variables. So the first experiment with Leslie cube, I'm not going to read them out. So if you're struggling, control variables, if you know what control variables are, you should be able to work out what the question is. I'm just going to give you 90 seconds for those two. Thirty seconds. Be quick if you haven't done. So question 5. Heat-proof mat is there to prevent or reduce conduction. So we're trying to prevent the heat loss through conduction from the Leslie cube. And the bung is trying to prevent heat loss through convection. So heat being lost by hot air rising from the top, so it can't leave the can if you've got a bung in. And when you're measuring the temperature of the infrared detector, you need to make sure that you're the same distance away from the surface and at the same angle. So 90 degrees, you don't want to be pointing at an angle. Picture there of a dog, infrared camera. You will have seen these pictures before. So using the temperature scale in degrees C on the right, what can you tell me about the radiation being emitted from the dog? 1 minute. Time up. So we've got eyes and open mouth there. We've got the highest temperature, probably around about 35. I would have thought using that temperature scale. Between the eyes, probably about 30. So we've got certain areas of that dog that are emitting more infrared radiation. So if you think about that, the eyes, the open mouth, and just the inside of the ears there's less insulation. So you've got a direct view, if you like, of those surfaces. So we can say those areas are emitting more infrared radiation. So the hotter an object, the brighter the colours that you get from that camera. So this is, well, I think it's an interesting question. So traditional desert clothing can be black or it can be white. You'll see both. So using what you know about absorption and emission of infrared, how can it be possible that both black and white is useful? I'm going to give you a minute, but in 30 seconds I'll put a little hint up. 10 seconds. I'll be impressed if you've nailed this. So, if I was stood out in the desert and I was in full sun, it's pretty obvious which one I'm going to choose. I'd choose white, because the black is a better absorber of heat radiation. You'll know that wearing your black school pants, sat out in the sun, it gets hot because it's absorbing that infrared radiation that's coming from the sun. So if I'm sat in the sun, I choose white, because it's reflecting, not absorbing a lot of the infrared. However, if you live in the desert, you wouldn't spend that much time directly in the sun. You'd often be in the shade, or at night. You're not in direct sunlight. So therefore, that's not an issue, is that absorbing the infrared. If you're actually hot, then the black will emit infrared radiation from your body faster. So therefore, it can be cooling if you're not in the sun to be wearing black. I'll leave you with a summary. So we've got a little summary of where infrared falls. We've got the main bit of the practical with Leslie Cube. We've got a little bit of applications about teapots and pipes at the back of your fridge, and a little bit about absorption. So pause the video if you want to make some further notes on that summary. Thanks for working hard with that, and I'll see you next time for another Waves video. More to come.